Do you know what this tool is? How about this one? These are two tools that are very important in making observations about circuits. Hi everyone, I'm Mr. Pinola, and today we're going to use these two tools, voltmeters and ammeters, to make some important observations and develop a key law in circuitry. But first, let's make sure we understand what the point of each of these tools are. We'll start with this tool. This tool is called a voltmeter. Can you guess what its job is? It measures voltage. That seems to make sense. A voltmeter measures voltage. It goes hand in hand. But how about this tool? This tool we said was an ammeter. What do you think its job is? Well, this one might be a little bit tricky, but let me see if we can just change one letter for a second. If this was written as ammeter instead of ammeter, would you now know what it's measuring? I'll give you a hint. Think about units. If you said electric current, you'd be correct. That's because electric current is measured in the unit of amps or amperes. So an ammeter, yes, it is spelt like this, measures electric current. We're going to see if we can use the voltmeter in conjunction with the ammeter to make some important observations about current. So now we have a circuit set up in front of us, which is going to enable us to make some measurements. Here is a resistor. Remember, every circuit not only needs a voltage source and some conductors, but also a load or a resistor that I'll put in. So I'm going to hook this resistor into my circuit. And I'll notice that my ammeter and my voltmeter both now have given me readings. What is the ammeter reading? Well, if I look closely, it looks like it is reading 0.045 amps or 45 milliamps. But I'm going to use the SI unit, so 0.045 amps. That's the current, and I've written it down just like any good scientist would. Then I'm going to come over to my voltmeter. What is it reading? It looks like it's showing me approximately 4.5 volts. So the reading on the ammeter was 0.45 amps, and the reading on the voltmeter was 4.5 volts. Before we move along, I want to prove a point to you, and I have this washable marker that will help me do just that. I'm going to make a mark on my ammeter in red, roughly where the ammeter needle came up to. I'm going to go over on my voltmeter and I'm going to do the same thing. Now I'm going to change out the resistor. I'm going to take this first resistor and I'm going to replace it with a resistor that has a higher amount of resistance. So I'm going to unplug it and you should see the current go down. That's because there's nothing flowing through. The voltmeter still reads the same thing because it still has the same 3 batteries. And here is my new resistor. Take a look at my new reading on the ammeter. It is significantly less than it was before. In fact, if I take a close look and I get the actual reading, my ammeter is now reading a current of 0.011 amps. Very, very small. My voltmeter Still has the same reading, 4.5 volts. That makes sense because I didn't change the voltage source. I still have my 3 batteries. And notice the voltmeter with the wires in the green is just simply hooked up to either end. So the rest of the circuit isn't really affecting the overall voltage. But we've made a very interesting observation here. Clearly, as the resistance went up and we put in a resistor that had a higher amount of resistance, the amount of current has decreased while the voltage remains the same. I think we can pretty safely conclude that resistance and current have an inverse relationship. More resistance means less current. Now let's do a similar experiment, except this time I'm going to treat resistance as my constant value. I'm going to keep this resistor in the circuit, the one that currently gives me a reading of 0.11 amps. However, this time I'm going to make there be less voltage in the circuit. Right now there's 4.5 volts, and that's by account of the fact that there are 3 batteries. Let me remove the middle battery and place it aside. You should notice that the needle for the voltage has now decreased. It's now only reading a voltage of 3 volts. That makes sense. We only have 2 batteries instead of 3. But look at what happened as a result. The current went down. It might not be a super dramatic increase, but we can clearly see that as the voltage decreased, the current decreased. If I add that 3rd battery back into my circuit, we'll see the opposite effect. Voltage went back up and current went back up. Clearly, voltage and current have a direct relationship, provided that resistance stays the same. More voltage yields more current, and less voltage will yield less current. So now let's dive into a little bit of math about this. We were trying to see what factors would affect current, which is given the symbol, as we've spoken about in mathematical equations, of I. Our equation is going to take the form of a fraction. As you might remember from previous units, anything that's on top of the fraction is going to be something that has a direct relationship with current. Just like in any fraction, if the numerator gets bigger, the answer gets bigger. Do you remember which of those 2 factors, voltage or resistance, had a direct relationship with current? If you said voltage, you'd be right. That's because more voltage will cause there to be more current, as we just saw from our most recent demonstration. So I'm going to put a V on top. The V represents voltage, and as the voltage goes up, the current goes up as well. That's because voltage is in the top part, or the numerator, of my fraction. But what about the bottom of my fraction? The bottom of any fraction is going to be a factor that has an inverse relationship with the answer. That's because as the denominator of a fraction gets larger, the answer gets smaller, because you're dividing by a bigger number. Which factor had an inverse relationship with current? If you said resistance, you'd be correct. So I'll put a capital R to represent resistance on the bottom of my equation. This clearly tells me that current, or I, is equal to V divided by R. More voltage means more current, and more resistance means less current. And that seems to match with what we just said. This is a mathematical representation of the experiment that we just conducted together in this video. Did you know that this equation has a name? Maybe you've heard of the name before. It's named after a scientist who the unit for resistance is also named after, Georg Ohm, and it is called Ohm's law. Some of you taking technology class might already be a little bit familiar with Ohm's law, because it tells us the relationship between current, voltage, and resistance. Now, some people learn about Ohm's law in a different form. In fact, some scientists like to multiply both sides by R, and therefore express Ohm's law as V equals I times R. You might see this on your equation sheet. However, I prefer the form of I equals V divided by R. That's because it very clearly shows us that voltage has a direct relationship with current and resistance has an inverse relationship. This form might be easier to use mathematically, however. So it's up to you. As long as you understand what Ohm's law says, you can use either calculation form when doing your math. So now let's put Ohm's law to the test. I'm going to go get the data that we took when doing our experiment from before. Do you remember our first trial? Our first trial in the experiment had an ammeter reading, so the current, or I, that was equal to 0.045 amps. Do you remember what the voltage was during that trial? Well, the voltage came out to exactly 4.5 volts. And we hooked this circuit up to a tiny little resistor. In fact, let me go get it. This resistor right here. Let's say I wanted to know what the resistance of this resistor is. We could use Ohm's law to help us find out. Let's do that now. So to figure out what the resistance of this resistor is, we have to use the given information that we just wrote down. We obtained the current from our ammeter and the voltage from our voltmeter. And let's use Ohm's law. I like the form I equals V divided by R. But we're not ready to solve just yet. R is not by itself. So we need to do something to make that happen. Well, the first thing is that we have to get rid of the fraction. Most people think we would solve for R right away in one step, but that's not true. Instead, we need to eliminate the fraction by multiplying both sides by R. If I multiply the right side by R, it cancels out the R in the fraction. So my new equation is I times R equals V. Remember, that's just the other form of Ohm's law. So if you just wanted to start there, that's totally fine. Now, we still need to isolate R. So R is connected to the I by multiplication. We need to do division to undo that multiplication. So let's divide the left side by I and the right side by I. That leaves me with the equation R, or resistance, equals V, voltage, divided by I, current. We have successfully isolated I, and we're going to use this formula to now calculate the resistance of this resistor. So let's finish out our mathematics. We know that R equals V divided by I. So the resistance is equal to the voltage measured by my voltmeter, 4.5 volts, divided by the current that was measured through my ammeter, 0.045 amps. Getting out my calculator, I can do some math here. 4.5 divided by 0.045 gives me an answer of exactly 100. 100 what? Well, notice we did volts divided by amps in our calculation. That could certainly be an acceptable unit. But do you remember what the SI unit for resistance is? I'll give you a hint. I wrote the name of that somewhere on the board. That's right, it's ohms. So rather than using volts divided by amps, I'm just going to write my answer as 100 ohms. According to Ohm's law, since a 4.5 volt set of batteries gave us a current of 0.45 amps, That means the resistance in our circuit was equal to exactly 100 ohms. Want to see something interesting? The last time that we were together, we talked a bit about resistor color codes. And if I hold this up a little closer to the camera, you might see that there are some colors in this resistor. It might be a little hard to make out, so let me read off the colors to you. They are brown, black, brown, and gold in that order. If I were to use my handy resistor color code chart, those combinations of colors would give me brown, which corresponds to the digit 1, black, which corresponds to the digit 0. My multiplier would be 10, which is associated with brown, and my tolerance is 5%. 10 times 10 is a resistance of 100 ohms. So according to the resistor color code chart, this resistor has a resistance of 100 ohms. That worked from me doing my calculations. Ohm's law never fails. Let's try another problem with Ohm's law now. I've got another resistor. This resistor is brown, green, brown, gold. That corresponds to a resistance of exactly 150 ohms. I'm going to hook this resistor up to a circuit that has only 2 batteries, not 3. That means that I will get a voltage of exactly 3 volts. If I do that, what current do you think that our ammeter is going to read? Well, let's find out. We'll use the original form of Ohm's law, I equals V divided by R, because I don't have to reorganize this formula at all. It's already got I, or current, isolated. So now let's just plug in voltage, which is equal to 3 volts, divided by resistance, which is equal to 150 ohms, will get us our answer. I'll use my calculator to do 3 divided by 150, and I'm going to get an answer of 0.02 amps. You might wonder where the A came from, but that's just because I already know in my head the SI unit for current is amperes. Now I know my ammeter is going to measure in milliamps, so I could convert this measurement over into milliamps. If I were to do that, my calculation would show me a current of 20 milliamps. So if you were doing this calculation using the 3-step method, this would be a completely acceptable answer, and the one that I would want you to get. But since we're going to be checking our ammeter, which is calibrated in milliamps, we might as well keep in mind that 20 milliamps is the correct conversion of 0.02 amps into milliamps. Welcome back to the lab, where we're going to test the calculation we just did. Here is our resistor. We found that it has a resistance of 150 ohms using the resistor color code chart. And here's my ammeter and voltmeter. Remember, we're only using 2 batteries this time, so our voltage should come out to approximately 3 volts. And our ammeter should get us a reading of approximately 20 milliamps, or as we calculated, 0.02 amps. Let's plug in the resistor and see if Ohm's law is correct and we get the readings from our voltmeter and our ammeter that we expected. Notice that our readings are pretty much spot on. This reading from the ammeter is 20 milliamps, or 0.02 amps. And this reading from my voltmeter is right on 3 volts. That tells us that Ohm's law works. Current is equal to voltage divided by resistance. Before we wrap up today, I want to show you this tool. This is not a tool that physicists would use per se, but a tool that maybe a bicyclist might use, because these little wrenches will help them to adjust the gears on their bicycle very easily. But this particular model of the tool is very easy because we not only have 3, 4, 5, 6, 7, 8 different tools packaged into one. It's sort of like this tool. Do you know what this is? Maybe you've seen an auto mechanic using this before. This is actually a voltmeter, which measures voltage, an ammeter, which measures current, and an ohm meter, which is something I didn't demonstrate before, but something that would measure resistance, all in one. All you have to do is adjust where your prongs are and change the dial, and you will be able to make a measurement of either voltage, current, or resistance. This is a very handy all-in-one tool, and it has a name, as you might expect. This kind of tool is called a multimeter. And in fact, this is a digital multimeter because it gives me a digital reading, not an analog meter like I was using before. Multimeters, especially of the digital variety, are extremely helpful because they essentially act as 3 different tools in one. I hope you learned something today about circuits. We noticed that voltage and current have a direct relationship, and we noticed that resistance and current have an inverse relationship. We put those ideas together in Ohm's law, which I've written for you here on the board. And we also showed that we can make these measurements using ammeters, voltmeters, or ohm meters, or using one tool for different purposes, a multimeter.